Welcome to this explainer. Today, we're diving into some absolutely fascinating research by Dalia Raquel Bibas and Clement Vidal. Their recent paper, Managing Uncertainty in Life Detection, Venus and Mars Claims Compared, really gets to the heart of how science handles the incredibly messy and, let's be honest, often confusing reality of searching for extraterrestrial life. You know, when we look up at the stars, we all kind of want a simple, straightforward yes or no answer to that ultimate question. Are we alone? But as we'll see, the reality of space exploration is rarely that simple. It's filled with ambiguous data, fierce debates, and constantly shifting narratives. So we're going to explore exactly how the scientific community processes all that uncertainty, and we'll use two of the most famous planetary discoveries in history as our guide.
So here's our roadmap for today. We're going to cover 1, the high stakes of life detection. 2, comparing the Mars and Venus claims. 3, shifting strategies in space exploration. 4, best practices for the future. And finally, 5, building transparent verification pathways. Let's get right to it.
Section 1. The high stakes of life detection.
The authors point out right away that the pressure surrounding any claim of discovering alien life is just staggering. Finding life beyond Earth isn't just another routine data point, right? It carries monumental weight. We're talking about stakes that span across 4 massive domains: scientific, social, philosophical, and theological. Scientifically, it literally redefines biology. Socially and philosophically, it fundamentally changes our entire place in the universe. And theologically, it challenges some deeply held beliefs about humanity's uniqueness. Because these stakes are just so unusually high, any detection claim instantly attracts intense global attention. People don't just want to know if there's some weird chemical on a rock floating in space. They want to know what it actually means for humanity.
But here's the catch. What happens when the answer is ambiguous? The public usually expects this clear eureka moment, right? Like a flying saucer landing, a microscopic fossil, or a definitive radio signal. But we really have to ask how the scientific community responds when the data isn't a definitive yes or no. What happens when a probe detects something highly unusual, but it could just as easily be a strange, completely non-biological chemical reaction? While the authors argue that this ambiguity is where the real work of science begins, it's this messy space where evidence, interpretation, and public narratives all violently crash into one another.
Section 2. Mars and Venus Claims Compared. Let's take a neutral look at 2 highly publicized case studies. On one hand, we have the 1976 Viking experiments on Mars. These yielded some highly debated soil chemistry results that mimicked biological activity, but honestly, they could just as easily have been highly reactive dirt. On the other hand, fast forward to the 2020 phosphine detection on Venus. Here, a potential biosignature gas was found, but it might also just be produced by completely unknown volcanic activity. Now, these events happened decades apart on 2 entirely different neighboring planets, yet the authors link them for a very specific reason. Both yielded high uncertainty results. Neither gave us that instant eureka moment everyone craved. Instead, both sparked intense and sometimes pretty polarizing debate within the scientific community. They're basically the perfect historical mirrors, showing us that the search for life is rarely about immediate confirmation. It's a long, drawn-out process of interpretation.
And this builds a fascinating, almost universal life cycle for ambiguous discoveries. The story almost never ends on day 1 with an initial, highly publicized claim. Months later, as other scientists reviewed the data, you get intense critique. Years later, new tools and perspectives lead to a complete reanalysis of that very same initial data, and decades later, you end up with entirely shifting assessments of what was actually found. The authors trace this exact unfolding for both the 1976 Viking data and the 2020 Venus phosphine data. It's a totally predictable, cyclical pattern of scientific rigor kicking in to manage that initial uncertainty.
Section 3. Shifting strategies in space exploration. Now, these ambiguous results did far more than just cause a bunch of academic debate in scientific journals. They actually altered the entire trajectory of international space agencies. Institutional choices absolutely shape future research pathways. Look at the aftermath of the 76 Viking experiments. Agencies didn't just keep sending the exact same life detection tools to Mars. The whole strategy fundamentally shifted to focus on habitability. They started looking for the conditions that could support life, like water, rather than directly hunting for the microbes themselves. In stark contrast, the 2020 Venus phosphine data triggered a completely different reaction. It launched an absolute renaissance in long-term atmospheric monitoring missions and renewed exploration of Venus. The uncertainty itself literally became the catalyst for entirely new strategic roadmaps.
Moving on to Section 4, Best Practices for the Future. With these historical lessons in mind from Mars and Venus, if we're going to face more ambiguous detections, and let's be real, as our instruments get better, we absolutely will, we need a much better playbook. The authors outline 4 critical practices for this. First up, aggressively embrace open science so data can be widely analyzed by the global community. Second, ensure constructive follow-up. Don't just tear down initial claims, build upon them. Third, maintain cognitive bias awareness. We have to make sure our desperate desire to find life or even our innate skepticism doesn't cloud the data. And finally, careful framing. By implementing these practices, the scientific community can make sure that initial detections are properly framed as starting points, not final conclusions. This is so crucial because it prevents the public from feeling misled or losing trust in science when the narratives inevitably shift over the ensuing months and years.
Section 5. Building transparent verification pathways.
This brings us to the ultimate solution proposed by Bibas and Vidal for managing the inherent uncertainty of astrobiology, establishing a transparent verification pathway. What does this mean? Basically, having a clear, methodical roadmap for follow-up research that actively protects scientific credibility as new evidence gradually refines an ambiguous initial detection. When a strange signal is detected, we really shouldn't just throw it to the press and hope for the best. We should have a transparent, pre-established pathway of how that claim will be tested, retested, and refined. Science isn't a light switch, instantly illuminating the truth, right? It's much more like the slow, methodical paving of a road in the dark. By making that paving process totally transparent, institutions protect their scientific credibility, while the evidence gradually comes into focus.
So the crucial takeaway here is exactly what this quote from the abstract captures. Managing future life detections is less about eliminating uncertainty than about building transparent verification pathways. I mean, this is a massive paradigm shift for us. We really have to stop thinking that our advanced telescopes and rovers are simply going to eliminate uncertainty. They won't. If anything, they'll likely give us even more complex, confusing data. Our goal shouldn't be to demand instant certainty from the cosmos. Instead, our goal absolutely must be to build trustworthy, transparent systems for finding the truth over time, protecting our credibility as follow-up evidence refines the picture.
Which leaves us with a final thought for you. As you watch the news, you know it's only a matter of time before the next big breakthrough headline claims we've found aliens on some distant exoplanet or moon. When that happens, ask yourself, are you looking for a final conclusion on day one? Or, understanding the long history of Mars and Venus, are you ready to follow the transparent pathway of scientific discovery? Let that initial detection be the start of the conversation, not the end of it. Thanks so much for joining me for this explainer, and keep your eyes on the stars.